And Matthew is going to tell us about ab-initio solutions of the many-electron Schrödinger equation with deep neural networks.
With the glasses, are you okay? Like this?
Okay, yeah. Shall I move the glasses up? Okay, thank you. I don't even know what this means. Okay, good morning. I'm going to talk to you about something I never thought I would ever talk to anyone about, which is neural networks and machine learning. About a year and a half ago, a bit less now, I guess, I was a complete skeptic about this. Obviously, it's done some great things, but I also thought it's ridiculously overhyped, and it is ridiculously overhyped, there's no doubt about it. But these guys, David Fowl, James Spencer, and Alex Matthews, James is someone I had worked with before. He used to be at Imperial College, where I am, and I did some quantum chemistry with him. He's a quantum chemist with a PhD from Ali Alavi's group. They came to me, and they're now working for a company called DeepMind in London, which you might have heard of. If you've heard of AlphaGo, this machine learning program that beat the world Go champion, they did that. They also wrote a program that taught itself chess. They only gave it the rules, and it played against itself for a couple of hours, learned how to play chess well, and then beat all the world's other chess programs that have been developed over 30 years. So they're very, very good as a company at deep learning. They were acquired by Google. As far as I can tell, they have absolutely no financial model at all. They seem to be just there to generate headlines for Google, as far as I can tell. They don't make a product. But there's about 100 really smart people in London doing machine learning. And they've started a physical sciences team. And James, because he knew me, came to me because they were interested in trying to apply deep learning to calculating many body wave functions. And so that's what this talk is about. And despite my skepticism at the beginning, they said, well, we'll pay you. And I said, that's great. They only paid me half a day every 2 weeks, so I wasn't very deeply involved. But they also said, you have to sign all these documents saying you won't tell anyone what you're doing. They still haven't let me see the code. So I've never done a project before where I can't see the code. But apparently in Google, there's one giant repository, and you can't get access to one little bit of it without having access to all of Google's code. And they didn't want me to be able to write my own search engine. So anyway, it was fun. They're very smart people, all three of them. David and Alex have physics backgrounds. James is a quantum chemist. This talk is actually quantum chemistry, because we haven't got to physics yet, but we would like to. So first of all, what's the problem we're trying to solve? The problem with trying to get chemistry, and I include condensed matter physics in that, you might do it the other way around if you want, is that you need really surprisingly high accuracy. Quantum chemists talk about 1 kilocalorie per mole, which is 43 milli-electron volts per particle. When I was starting off in condensed matter physics, because I'm not a chemist, I'm a physicist, I never really believed this. I thought this was nonsense that only chemists say. But it's real, and the reason is I think that we live in a rather low energy world. KT is 25 millivolts at room temperature, and so if you're interested in anything happening at low temperature, you really do need these kind of low energy scales. So that's why it's true. I've also done quite a lot of work on energy differences between competing structures, especially with solid hydrogen, and there you quite frequently seem to see problems where 10 millivolt energy differences matter. It's really horrible. And if you're interested in magnetism or strongly correlated structures, the energy differences of interest can be smaller again. Okay? This isn't necessarily a problem, but it's a problem when you start from the Schrödinger equation. So here's the Schrödinger equation. This is our grand unified theory in condensed matter physics. So I'm going to use Di for ionic positions, Zi for atomic numbers. Solving the Schrödinger equation for n electrons is NP hard, at least according to very smart people like Matthias Treuer, and I see no reason to disbelieve him. So the best we can reasonably hope for in solving this are approximate results. Okay. we've already talked about energy scales. The problem is that in the Schrödinger equation itself, the smallest energy scale you get for the total electronic energy is about 100 eV. That's for a very light single atom. And it rapidly rises into thousands and tens of thousands of eV for molecules and unit cells of solids and things. A chemical bond's a few eV. A chemical reaction energy we need to pin down to about a tenth of an eV. And correlations of magnetism are even lower in energy. And so the Schrödinger equation is working at this crazy high energy scale, and we need, 5 significant figures to get things that a chemist would care about. This suggests that starting from the Schrödinger equation is a stupid thing to do, but unfortunately it's where we know to start. Yeah, you should perhaps be doing something cleverer. One thing that people don't often point out is that if you want these very tiny energy scales, let's say a tenth of an eV, that maps onto a length scale as well. Energy over the Fermi energy is about 10 to the minus 2 if the energy is a tenth of an eV. I'm saying the Fermi energy is 10 eV. That gets you a wavelength ratio of about 10, and so about 20 angstroms sizes. So if we want to get very accurate results, we also need to look at big systems often, unless you are looking at a molecule in outer space anyway. How can you do this kind of stuff? Well, DFT is amazing, considering it looks like a mean field theory. It can sometimes achieve chemical accuracy if you choose the right functional. There are, of course, a bewildering variety of functionals to choose from now, and if you know exactly which one to use for the problem you're trying to solve, you can do it. But how can you tell in advance what's the right one? And we also know that there's a lot. The one true functional is a very weird thing, and so it may be really very hard to home in on it in a general way. I mean, I understand a lot of people are dreaming of that, and DeepMind, I'm sure, are working on that, although they won't tell me what they do, apart from what I'm doing with them. But it's an obvious thing to try and learn the one true functional. Perturbation theory, we heard, for example, Xavier talk about that yesterday. That works really well for weakly correlated materials, better for excitations than energies, I think. It may not help you so much when you have a non-Fermi liquid behavior and you don't know where to start. A surprisingly stupid approach that works really well is just to guess the wave function. If you think about the very few non-Fermi liquid style problems that have ever been solved in any sense that we truly understand, they were mostly done by guessing the wave function. BCS theory is a guessed wave function. Laughlin's fractional quantum Hall effect, the beta ansatz, there are others. Yeah, so it's a stupid thing to do, but it's surprisingly successful if you're trying to understand something you don't know about. And of course, you can parameterize your guessed wave functions. And there are all kinds of different families of wave functions people use, from Hartree-Fock, that's just a parameterized wave function, a single determinant. Even you can think of RPA as a parameterized wave function if you want, although most people don't. The one I'm mostly going to be looking at here is the Slater-Jastrow wave function, but any of them will do in principle. And so one approach you can use is to guess a wave function in some form, one of these or a new one, which I'll present a new one today, and you can start trying to calculate energies and adjust the parameters to minimize your total energy. When I was a PhD student, my supervisor said to me, quantum chemists have got completely the wrong idea. Trying to parameterize a wave function of, say, 100 electrons, a 300-dimensional function, is the most preposterous thing you could even dream of doing. He believes that even as you let the system size tend to infinity, the wave function doesn't even exist anymore. And so he says you should obviously go for Green's functions or something, some integrate out many degrees of freedom. And probably he's right. But I've spent a lot of my career trying to do this because I couldn't think of anything better. So just a quick reminder of variation of Monte Carlo. It's how you deal with guessed wave functions, or one way. You guess a wave function, and I'm going to use big R for the wave function we've guessed. You calculate the expectation value of the energy in that wave function, and you can rewrite that integral, which is a 3n-dimensional integral if you have n electrons, plus a spin sum, in this form. I just multiplied and divided by psi. And then this part at the right here can be interpreted as a probability density, and this can be interpreted as a score. So this is like saying you throw darts into your configuration space, landing according to this probability density. Each dart, when it hits, scores this amount. We average the scores, and that gets us the integral. Okay, and that's Monte Carlo integration. And variation of Monte Carlo is nothing more than you guess a wave function, you evaluate this, you adjust the parameters in the wave function to try and lower the expectation value of the energy. And it works for any wave function. It's most often used in solids with Slater-Jastrow wave functions. Have we got a time? I have no idea how long I'm going on. Okay. So most of the work in large molecules and solids still is done with a Slater-Jastrow wave function, which is a very simple form. We take a Slater determinant, as in Hartree-Fock theory, and we try and correlate it by suppressing the value when two electrons get close together. That's pretty much all it is. And you can, of course, take linear combinations of these, lots of determinants. This is just because I've had too many slides without a picture. This is some work I did ages ago with Slater-Jastrow wave functions. I was looking at an electron gas with an external potential applied to it so that the electron density looked like a sine wave, more or less. And you put an electron in the bottom here, where the density is low, and you look at the exchange correlation hole around it as calculated with the wave function, and it looks like this. You can't dig out a hole where there are no electrons, so you would dig out the hole in these regions either side where there are electrons. The LDA, of course, assumes you're in a uniform electron gas, so this just shows you how silly the LDA can be in some cases. So this is a very useful method, and it's the basis of most Monte Carlo methods for real solids rather than model solids. But it's not normally capable of chemical accuracy, even in weakly correlated systems. You can do much better by starting with this wave function, then doing a projector method to get close to the ground state. Diffusion Monte Carlo is one, auxiliary field Monte Carlo is another. And it's not obvious how to extend this form when it doesn't work. You could try linear combinations of determinants, but that doesn't scale with system size at all. You get exponentially more determinants required as you grow the system. And it's again no help when the physics is wrong. So where the DeepMind people started is the observation that artificial neural networks, this is not very good. This one is not working at all. Yeah. Oh, it's even worse. Okay. Artificial neural networks are flexible and efficient function approximators. That's all they are. You put in a number, you put in a bunch of data, out comes a number. That's what a neural network does for you. And so perhaps we can represent the wave function as a deep neural network. So we are abandoning the idea of having an explicit functional form, and the wave function is encoded in all the weights that link the layers of our network together, and all the biases we enter there. The second observation, which we came up with together, is that nothing requires the orbitals in a Slater determinant to be functions of the coordinates of a single electron. Now, that's already known. There's a thing called backflow wave functions that goes back to Feynman work on liquid helium, but we were looking at it again here, in a more general way perhaps. The only requirement is that if you interchange two of the variables, Ri and Rj, that interchanges, in this case, two columns of the determinant. Okay? And what that means is you can replace the orbitals in the determinant by a much more general function of all of the positions of all the electrons. So it's got one electron singled out, and then it also depends on where all the other electrons are. So this is Rj, and this is the set of Rs excluding J. Okay? And as long as the dependence on all these other Rs is such that if I flip a pair of them around, the wave function doesn't change. So it's got to be symmetric under interchange of all these other ones. This determinant is still antisymmetric. You can go think about that afterwards. It's true. Okay. So this gives us a way of generalizing the idea of a Slater determinant, where the things inside are now functions of all the electron positions. And the main thing we did is build a neural network, or they did, is build a neural network to construct these permutation equivariant kind of determinants. So this is how it works. I thought I'd better remind you what a neural network is, because I guess not everyone will know. And honestly, I know almost nothing about this part of it. But a very simple neural network looks like this. You have some inputs. They go into these things, which you can think of as neurons. It was originally developed to model the brain. These inputs are now connected. Inside, we have another layer of neurons, not necessarily the same number. And the inputs are connected to all of them by numbers. So, for example, to get the new input on this purple neuron, we add the inputs together on all the 4 input neurons, weighted by numbers, which are sort of a strength of the connection. Okay, so it's essentially a linear operator. We take a matrix, and we multiply that matrix by the inputs on layer L, and we get the inputs on layer L plus 1. We also can add a bias. So far, this is just a linear transformation. These 4 numbers are mapped by a linear transformation to these 5 numbers here, and then to the 1 output number. If we have many such hidden layers. If we had just linear transformations, obviously the composition of linear transformations is another linear transformation. That's not very interesting. So once we've done this mapping, we multiply by something called the activation function, which was originally meant to model a neuron. Yeah, the idea with the neuron in the brain is if the input is low, it doesn't fire. If the input exceeds a threshold, it fires. So this activation function was originally something that would look like this. It was a step function. Now we need our functions to be differentiable, because otherwise expectation values of the Hamiltonian, which involve Laplacians, are bad to do. So we make a smooth activation function. It's a tanh. But that's what this is. So that makes it nonlinear. And if you have enough layers, this is a general function approximator. And you can learn the parameters, all these parameters inside the W's and the B's, by having a target output and trying to essentially just adjust the parameters until your output approaches the target. Okay? And there are very efficient ways of doing that using automatic differentiation and backpropagation, tricks that I won't talk about. So in our case, the inputs, the simplest way of thinking about it is that the inputs are electron positions. They're in fact not just electron positions, and the output is a wave function. Our objective, our loss function, as they call it in the field, is to minimize the expectation value of the energy. Okay, so that we adjust the parameters to do that. So to do it then, we have to do it with Monte Carlo. We sample points from these four positions, in this case 4 electrons, from the current wave function squared using Metropolis algorithm. We then evaluate, we accumulate a bunch of points, a batch of points, and we estimate the energy. Then we adjust the neural network parameters to minimize the energy. That's all it is. This is the real network we use. Yeah, this is a very scary diagram, so I'm going to break it down to try and implement that wave function I showed you before. I don't think you can see this, so I'll try to say, let's concentrate on the top region here. This is for spin-up electrons, and this is spin-down, but let's forget spin. So this yellow block here are all the input parameters that involve electron 1, only electron 1. So they involve the separation of electron 1 from nucleus, I, okay, for each nucleus. So we say how far is electron 1 from all the other nuclei, not just the distance, but the vectorial separation. We also put in the modulus of that vector. I'll explain why in a second. So those are our input parameters for electron 1. We have similar for electron 2 and up to electron n. And we also put in all the electron separations, vectors, and the moduli of the vectors. So they're all input parameters. And they essentially propagate through the network layer by layer. Let me just actually jump on and say what the input parameters are. So that this first vector across here, or the ith vector across here, is all the input parameters involving only electron I. And they involve the separations of electron I from the nuclei and the moduli of those separations. So all these numbers just depend on our I. We put the moduli in because although our neural network is completely differentiable, wave functions are not. Where you're at a nucleus, there's a cusp, okay? And so if we can't represent that with a completely differentiable neural network, but we can if we put in this data, because it's a differentiable function of the modulus, which is itself got a cusp in it. As the data propagates through the network, we go through various layers here. You can see we're feeding information from other electrons into the first one. So this is, for example, electron I here. And so as we propagate through, we're feeding in information about all the other electrons, and we do it in such a way that it generates a function of this type, so that the information of the other electrons that's fed in is symmetric. If I were to interchange other electrons, I would still get the same thing. And so what we're in effect generating at the end of this process is one of these functions of Ri and all the other Ri's that go into our generalized determinant. And the final step then is to make wave functions by just doing a dot product essentially with these functions that we generated in the neural network. Okay, so we end up with a whole bunch of functions which look like the things we can put in Slater determinants, and the final process is to evaluate the determinant of those. We don't need a Jastrow anymore because that's built in to these functions already. One of the other technical developments we did is that you need an efficient algorithm to minimize the energy. And the standard machine learning algorithm, the simplest one, is called Adam, and this is how it goes with the number of iterations for one of our examples. We use something instead called KFAC, which is actually what people didn't seem to have realized is that Monte Carlo people have spent ages trying to evaluate efficient wave function optimization algorithms. One of them, due to Sandro Sorella, is called stochastic reconfiguration. Machine learning people had invented essentially the same thing, and they call it natural gradient descent. They're nearly the same. And KFAC is a machine, or an already existing machine learning approximation to natural gradient descent, which makes it much more efficient. Okay, it's an approximation. And so we found that essentially we're using stochastic reconfiguration and it works really well. Okay. Don't know what's happening. Okay, so I had a little movie here that just shows you, I don't think I have time to show it, but it shows you, this was, I think, a lithium, can't remember, unless it was an ethene molecule, I think, showing, we started with an initial wave function, you can see the two carbons there, and we're watching the network learn the molecule, and it's concentrating more weight around the carbons. I won't show it because it's not actually very interesting. Okay, so let's look at some results of this. This is one determinant. This is a conventional VMC code done well by someone called Priyanka Seth from the Cambridge group for various atoms. We also implemented a purely Slater-Jastrow neural network, and we're slightly outperforming the original Slater-Jastrow. I think that's because our Slater-Jastrow neural network has a very general Jastrow factor in it and completely optimizes the one-electron wave functions with no basis set limitations. I'm not quite sure, but we slightly outperform Priyanka there. This is one determinant of our new kind of Fermi net wave determinant, and this is chemical accuracy, so we're not quite there with one determinant. If we go up to 16 determinants, we're well within chemical accuracy for all these atoms. And Priyanka has also gone up to tens of thousands of determinants, and it takes her tens of thousands of determinants to get to where we get to in 16. So it's much better than a standard CI expansion. This is what happens when you add determinants. These are some molecules. You're watching the energy drop as you add the add determinants, and this is a CCSD energy, couple cluster singles and doubles, which is really the best quantum chemical method that scales to reasonably large systems. So again, we're doing very well there. This is an interesting example. It's a very trivial example of a little rectangle of hydrogen atoms with an angle here, theta, that's used to parameterize it. The diagonal of the molecule of the rectangle is kept fixed in length. And this is a small enough system that you can exactly diagonalize it with couple cluster. With full configuration interaction. And that's the green lines here. That's a full configuration interaction calculation. This one slightly below it is our line. Both methods are variational. They're both variational methods, so we're slightly beating full CI there. I think that's because full CI has a restricted basis set, and we don't. Ours is in the continuum. This is what coupled cluster gets. Absolute nonsense, yeah? It's because coupled cluster is a single reference method, and this is essentially a two-reference system. So it's a mean example for coupled cluster. We specifically chose it to be mean. Coupled cluster is also not variational, so the energy can come out lower. Here's some molecules. This is a nitrogen dimer. This is quite a hard one for standard quantum chemical methods. And you can see it here. This is the calculated energy versus the experimental energy as a function of bond length. And as you're breaking the bond, you run into trouble with many methods. They become, again, quite multi-configurational. And this is a couple cluster. And you can see that it really is quite bad. This is us, and we're slightly better than couple cluster, still not perfect. I did want to point out that I perhaps didn't say for the atoms, that when we do the best job we can, which is 16 determinants of our funny determinants, we can get to within typically 99.8% of the correlation energy. A good VMC calculation normally gets 85% of the correlation energy. So we orders of magnitude better. And that's, okay, I can do it. That's up to the DMC kind of level of accuracy or beyond. And also a couple cluster level of accuracy or beyond. Here's a bunch of molecules we did. It's not really very interesting to see what they are, but look at these correlation energies returned by a simple variational method with always 16 of these determinants. Well above 99% in all cases. So you might say, well, quantum chemists can do this for this tiny kind of molecule, but their methods do not scale. And at least conventional VMC scales really well. You can do thousands of electrons with conventional VMC. Whether we can do that with this kind of VMC, I'm not yet sure. But that's the dream. And it's not unreasonable to hope that we can. We didn't do very well for this last molecule. I think that's because we didn't actually do it right. We haven't quite got it going yet, but we're not sure. And the other thing is that we are at least as good as coupled cluster, or comparable to coupled, really very close to coupled cluster for all of these, which is, quantum chemists would say, is a good method. We also did the H10 molecule, so that's 10 hydrogen atoms in a row. That doesn't sound very interesting, but it's become a standard benchmark in quantum chemistry, and there's a great paper by, what's the lead author called, Mario Motta, which synthesizes results from almost every method anyone's ever tried for doing many-body quantum mechanics in real systems with real atoms. And as a function of the separation, this is data from their paper to which we added one line, which is ours. Okay, so there's Ferminet here. Green is what they think is the right answer, somewhere in green. And we're really very, very, very close, and better than most of these methods, like coupled cluster, better than auxiliary field Monte Carlo, and well, similar to auxiliary field Monte Carlo. The thing is that most of these methods has been in development for 50 years. We've been at it for 1. So I think there's hope that we can actually do better than these things. And also, the wave function we come up with is perfectly good as a starting point for any kind of other projector Monte Carlo like DMC or auxiliary field Monte Carlo. So that also might prove useful. We haven't done any of this yet. Yeah, I've never talked about this before. So to summarize, this new wave function we come up with is way better than any other form of VMC that I know of that you can apply to large systems. And it's way better than just trying to do VMC with a Slater-Jastrow wave function and expanding in tens of thousands of determinants. It rivals coupled cluster for equilibrium geometries, where coupled cluster is known as the gold standard of quantum chemistry. I hate that phrase, but it is. And for molecules with a strong multi-determinant nature, it outperforms it easily. It can serve as a trial function for diffusion Monte Carlo and other projector methods. We've only just, that should say, begun. So we have still a long way to go and a lot of improvement can make. If only the DeepMind people were less focused on headlines and more interested in real science, I might be more confident about how it's going. But they are planning to open source the code. And at that point, I and the rest of you will at least be able to see it. Yeah. The only thing I would like to say is I've worked with James Spencer a long time, and he's one of the most honest scientists I know. So I do trust the result. They're not kidding us. But I haven't seen it myself. So questions. How general is this wave function? It looks a bit like what's called iterated backflow, which you can argue is a general way to get to a ground state wave function. But I'm not sure about that. I haven't managed to prove it one way or the other. In other words, could in principle, if we had enough layers, currently we only have 4 in our deep, not very deep neural network. If we had enough layers, could we actually get the right function in principle? I don't know. If not, can we really get away with just a few of these determinants? All these results were with 16, and the same hyperparameters everywhere. What are the limits to the accuracy? Can we do solids? I see no reason why not, actually, but we haven't yet. Slater-Jastrow variation of Monte Carlo is size extensive. That means if you take 2 atoms far apart, and then 3 atoms far apart, and 4 atoms far apart, the energy just doubles and triples and quadruples, in proportion to the number of atoms. We have had some minor trouble with that, like when we're pulling away molecules apart. I think that's because we haven't got any notion of locality in our codes yet, and I think we can put it in, but it's not completely obvious to me that will work. I would like to put locality in because I believe correlations are local. I'd like to know the fact that electrons here don't really care about what electrons far away are doing. And how does the big question is, how does it scale with system size? If this is just for tiny molecules, quantum chemists can do it already. The reason I'm interested is because Slater-Jastrow variation of Monte Carlo scales really well. You can easily do thousands of electrons, which is big enough to get very accurate answers if only the method were better. Perhaps this can do the same. We haven't done it yet. The best we've done is some atoms scaling up with numbers of electrons. I have to admit we don't get good results for these heavy ones yet, but we can do it. And if you fit curves to these, it seems to be, there's no real difference between a cubic fit and a quartic fit, which suggests that it's a cubic, okay? And we have theoretical reasons for believing it's cubic scaling anyway. But this scaling is misleading because this is just the scaling for one evaluation of the wave function. It doesn't tell you, for example, as the system gets bigger, do you need more layers? Do you need wider layers? does it take longer to converge to the ground state? But anyway, I think this is really quite a promising thing, and I'm less skeptical about the value of machine learning than I was a year ago. Thank you.
Thank you. Thank you very much. Fascinating talk, Matthew.
Thank you.
Other questions? Okay. I have one to start. Well, Xavier is volunteering there for the first question.
Well, at the level of scaling, already at, when you have your input, you enter all the distances between electron and nuclei.
So the input, the input's n squared.
N squared already. Okay.
Yeah, but
so you can.
But the bottleneck is still formally the determinant evaluation, which is only n cubed.
N cubed.
Okay.
And why would then get quartic?
Oh, this was just to see whether it was quartic.
Yeah.
Okay, so the real question is, is it much harder and does it take much longer to reach the ground state when you're in a big system? There are also memory problems possibly, because there's a lot, these are big neural networks, there's a lot of data and there are tens of thousands of parameters. And so that's another possible issue. I'm not worried about the scaling of one evaluation. That's not what scares me.
Okay, well, thank you. It was
Okay.
very interesting.
Yeah, thank you.
There was another question, Andrew, yes?
Hi, Matthew.
Hi.
I enjoyed everything about this talk, but I'm not sure how well I understood it now that I think. Is the method learning or solving? Suppose you have a type of chemistry that you don't expose this to, that you never show an sp2 bonded carbon. You just have sp3 bonded carbons when you're running it. Will it know how to solve for benzene, or would you have to say, I didn't teach it benzene, I better go back, this kind of thing?
So this is not learning from data. This is learning from the variational principle.
Yes.
So it is completely general, and we haven't put in anything. We do often, to minimize, to speed it up, we often start with a kind of Hartree-Fock-like wave function, a neural network. But we can do this with knowing nothing for a new system. So it's not learning in the standard machine learning sense from data.
Yeah, that's more like solving.
Yeah, it's more like solving. So maybe I should call it solving.
Okay, I think I understand it a little better now. Thank you.
Thank you.
More questions?
Do you find local minima?
So
what are the meaning of this local minima?
Yeah, so I mean, it's obviously something to worry about. You do find them in other kinds of variation of Monte Carlo. We have not been troubled with them. And I think these giant machine learning things, when I was a grad student, I was taught that you should not overfit. Yeah, you should have just this minimum number of parameters. And there's a famous quote that if you have 5 parameters, you can fit an elephant. We've got hundreds of thousands, well, tens of thousands of parameters in here. So it's vastly over-parameterized. And actually, in a weird way, that seems to help because it seems to make it harder to get stuck in subsidiary minima. There's always another dimension you can escape along. And so we have not been troubled with subsidiary minima, no. And I think machine learning people often say that that's how it works. So we can't guarantee that we won't. It's a straight downhill minimization method, but of course there's a lot of noise, and we gradually reduce the learning rate, the step size as we go. So it hasn't been a problem, that's all I can say. And we start in a sensible place as well, because we know some physics and chemistry.
Another question over there, yes?
Hiya. I just wanted to confirm my understanding about something. You're using the Slater-Jastrow form. You're using the Slater form specifically to enforce anti-symmetry on the wave function, because presumably it would go to the bosonic ground state if you let it with just kind of do a general many-electron wave function.
Yeah.
Have you tried other ways of kind of enforcing anti-symmetry on your neural network, or is this just kind of the most sensible one?
We haven't. I mean, this is all we've done. There is some work I can't remember where it's from. There was one paper which had a different form of antisymmetric wave function, which I thought was physically nonsense. It was antisymmetric and proved to be physically nonsense because it got very bad results. I don't know many other ways of representing antisymmetric functions, actually. If you do, tell me them, because the antisymmetry is the big issue here. This is the thing that makes this new. People haven't done antisymmetric neural networks for fermions before. Other people are trying very similar things now.
Sure.
But yeah.
Thank you.
Miguel again? Oh, no, Aaron was finding. Yeah, there is somebody else first.
Thank you for the talk. A very late question. Do you get rid of the fixed node approximation here, or it's absolutely irrelevant?
Yeah, so the fixed node approximation affects diffusion Monte Carlo. Yeah, so in diffusion Monte Carlo, you start with a trial function which has a nodal surface. That's the surface of zeros, where the wave function is 0. And diffusion Monte Carlo finds you the very best possible wave function. It doesn't find it explicitly, but it samples the very best possible wave function with that fixed nodal surface. What we're doing here is nothing like that. This is completely variational. So we're just adjusting a trial function to get the lowest energy, so that there's no concept of a fixed node approximation here. We could use these wave functions in diffusion Monte Carlo, and if our nodal surfaces are actually good, we would get better diffusion Monte Carlo results than other people. But we haven't done that yet. Okay.
Thanks. I have a question myself.
Yeah.
You were talking about 16 Slater determinants at some point.
Yeah.
Is the way of improving your calculations with adding Slater determinants, would it be the traditional conventional way that quantum chemists would do? Or do you have different ways of improving?
So we don't do it the quantum chemistry way. We don't take a basis of one electron functions and optimize, and do a linear combination of them and optimize the coefficients. We explicitly run the neural network with calculating a bunch of Slater determinants at the end with arbitrary coefficients. And that everything is optimized at once. So our Slater determinants are not orthogonal. Goodness knows what they are, but 16 of them can do the job of 10,000 ordinary ones. Yeah.
You don't have to predetermine anything. You just say
nothing.
16.
Yeah, we just say 16. We want 16, please. And okay, these guys they're very clever. They worked incredibly hard for over a year. It's not easy. Actually, the TensorFlow is a mess and it keeps crashing and things. So.
Gail had another question there. Oh, and Mike. Well, let's start with Mike.
Maybe this is stupid. It was related, I think, to Emilio's. But why do you need more than one determinant? Haven't you got flexibility in the symmetric 2 to n electron?
So that's one of the questions we haven't answered yet. Is one determinant in principle enough? In other words, if we make our functions general enough, could we get anything? Yeah. The answer is I don't know. In practice, we used more than one because it helped. But that might be because our neural networks they're only got 4 layers thick, so they're not very general function approximators. So it might be that actually we just haven't tried hard enough. The answer is I actually don't know. It's a question that's on our to-do list to try and figure out.
So there was a question there, then there is Miguel, and we have the time, Xavier.
Thanks for the very nice talk. I'm from Alavis group, so I might ask something about this multi-determinant. So this idea of using a general many-body function in the Slater determinant, I think it's the biggest invention here. And if I understand correctly, so by doing this, we actually cure this electron-electron cusp condition, right? But do you also think that it sort of helps with like entanglement that happens when you need a lot of Slater determinants to get the wave function correct?
So are you talking about what a chemist would call static correlation, or just entanglement?
Yeah. Static. Well.
So essentially it's Mike's question, and the answer is I don't really know. What we do know is that we can do much better. We can get away with many fewer determinants than you would use in a standard quantum chemistry code. for systems that are multi-determinantal. But so it does help, but whether it helps a lot, I don't know. You know, if we take a strongly entangled system, yeah. Another way to say this is if you come this from the kind of tensor networks background, they say that they can do it if the entanglement is low, and they can't do it otherwise. Does the same apply here? I wish I knew. I actually don't know.
But actually, are you devising like serious comparison between like how much compression that you get from using the neural network for describing the strong correlations? Like you, for example, in FCA QMC, you need 10,000 slated determinants to represent the strong correlations.
Yeah.
But now, with this Fermi net, like the compression rate.
Well, all I know is that for all the molecules I showed you, up to bicyclobutane, and we did N2 and other ones that chemists work at, we got away with 16. And we're within chemical accuracy almost always. That's all I know.
Okay, thanks.
If I knew more, I would tell you. I'm not hiding stuff.
So, very stupid question. Let's imagine that you manage to do the couple of thousand electrons and you can make a solid. Could you get superconductivity and things like those?
Are we down at the energy scale for superconductivity? Probably, well, maybe for high temperature superconductivity, not for low temperature superconductivity. I mean, we're at millihartree accuracy. I don't think that's quite enough for. Yeah. So, but in principle, I don't see why not. Yeah. I mean, certainly the BCS wave function doesn't look, if we're thinking about BCS, doesn't look very different from what we're using if you think about it. So.
Okay, very last question.
A comment, of course, you can extend to the nuclei motion with electrons. It's about, yeah.
Well, come on, this was hard enough. Yeah, doing a nitrogen dimer.
It's okay. My question was more realistic. Have you tried, and can you tell us about 2-stage, 3-stage, and 4-stage? 4-stage network is what you are doing, but what about the results with only 2-stage neural networks?
I don't think we have done enough to really know.
You have really tried? It was 4 from the very start?
Yeah, we just chose 4, and we decided not to increase it because it was just painful. So the biggest problem, the biggest technical problem we faced was
kind of a convergence parameter.
Yeah, no, I mean there's an awful lot we haven't done yet. This is quite early. We haven't published anything yet. We submitted a paper that got bounced, so we'll resubmit it. We submit it. We made a mistake and sent it to Nature. So we're going to resubmit that. But this is the first talk about it, and it's all very, very new. And there's obviously many things to do. Yeah, if it's wide enough. Yeah. But yeah, so we also haven't really investigated the width either.
Okay, thank you very much again. That was really very, very interesting. We thank the speaker again.